You know what that is? That is a big, fat cable carrying current. Okay? So like, here is all of my current coming out of the page. I'm gonna draw like a bunch of dots. Right? Okay? Those dots are the current flowing in this big thick wire flowing out the page towards you. Okay? Now, can you guess what I'm going to ask you to solve for? You say, oh no, he's going to ask for the magnetic field inside the wire, isn't he? Right? I'm going to say, hey, this is a wire that has a radius big R. Okay? All right? And I want to know the magnetic field strength at some point here inside, right? Okay, at some point here. Okay, at some point that is a distance little r less than big R. Okay? For wire of radius r with a uniform current density. Carrying a total current I. Okay, total current I. Find V at R less than R. Okay, there we go. Okay, so I can see there's a couple things I need to introduce here. Okay, so we're trying to find the B field there. Now, I actually talked to you really quickly about current density and what that means. What do you think current density, I can't believe I left the S out. What do you suppose current density means? Density in general, we think of it as like in terms of volumetric mass density is what we usually think about, my mass per volume, right? How tightly packed mass is. We've done this with charge though too. We've talked about how much charge there is per volume, right? My volumetric charge density. We've talked about charge per area and all that stuff. Now I'm talking about current density, so that'd be like current per area. That's like, here's all these charges flowing in this wire. How much current do I have? How many amps of coulombs per second flowing per square centimeter? You know what I mean? Or per square meter. That would be my current density. So current density, let's define that. Let's not define that there. Let's define it somewhere out of the way. Current density, we're going to use the symbol capital J. Okay? And so capital J is just my total current divided by the area. Okay? So it's like how densely packed that charge is flowing down the wire. Make sense? Okay. We actually came up with this, I believe, we saw this when we talked about resistance and resistivity. Right? And we derived Ohm's law from E field strength, right? I think we talked about that, how you need a bigger E field to get a stronger current density flowing down the wire. I think we introduced this back then, if I remember right. Okay, that was in that video that I asked you to watch, right? That I didn't do live in class, but I was like, hey, watch this one. There's one video from the circuits unit that I was like, just go ahead and watch this one. I talked about the sub-microscopic model of current. That video is where that came from. Anyway, but that's where you would see that. Okay, it's an old video that I made last spring. But anyway, we then post it here. So, okay, so that's it. So the point is, here we're saying it's a uniform current density. So what's that going to let us do? Well, here we go. We want to find the magnetic field here. So we're going to use Ampere's law, and we're going to choose a path that passes through that point, right? What's my path have to be like? Well, the path has to enclose some charge, or some current, going through the membrane bounded by the path, and it has to be a complete loop that ends up back on itself, right? Okay. I know what my magnetic, first of all, I probably should have sketched the magnetic field first, right? Magnetic field lines loop around currents, right? So magnetic fields are going to loop around like this. It makes sense, I think, that inside it's going to be continuing to loop around like this. So inside here, I have a magnetic field here looping around like that, inside, yeah, and outside, right? And the field lines should get farther apart as we go out, right? Because the field's getting weaker. So the point is, I've got field inside the wire as well as outside. Okay, kind of makes sense. There's current going in. Well, according to this equation, if I have a closed path and there's current going through that path, this B dot DL had better not be 0, right? It's got to add up to be how much current goes through it. So here we go. So I'm going to choose a path that goes right along the field line, right? This is my Amperian path, like a Gaussian surface. It's a path I choose to do this integral over. Okay, so I'm going to just do a circle that goes along the field line there at radius little r. So when I do this, you say, hey, that cosine theta, it's going to be, once again, I'm going with the field line at every point, it's going to be cosine of 0. And the B is going to be uniform by symmetry. You expect the same strength anywhere that distance out. So the B is going to be a constant come out of the integral. I'm going to have cosine of 0 degrees. And so I'm just left with the integral of dl. And you say, hey, the integral dl, I know what that's going to be. That's just going to be the distance around that circle. It's a circle with radius little r. That's just 2 pi little r. Right? Now I go to the other side. Mu naught times my current n. This is the tricky part now. All right? Well, mu naught's not the tricky part. We say, figuring out the current that went through this. Now, if I told you J, if I gave you the current density, then you say, what would it be? The current is just the current density times the area. It'd just be J times A. And I could write in the equation for the area of that circle, right? And so you'd say, oh, okay, hang on a second. I'm going to do it one way, then I'm going to erase it. If I gave you J, it would be JA, right? Because you say J is I per A, so I is AJ. Yeah, or JA, whatever you want to say, right? Okay, and that would be it. And then I would just take, if that was the case, then I just move my 2 pi r over, right? The area would be what? Area of the circle is pi r squared, right? So I could write this then as mu naught J, and it'd be what? Pi r squared, right? And down here I'd move the 2 pi r, right? I'd move that down there. Sorry, I'll do the next line. So my B would be mu naught J, and I have pi r squared over 2 pi r, right? And you say, okay, the pi would cancel, and one of the r's would cancel, and I would get my B field to be equal to mu naught J times over 2 times r. Okay? However, I'm going to be mean, and I'm not going to give you J. Okay? What if instead I just told you it had a total current I, and that's a uniform current density? Okay? So remember mu naught J over here. So what's it going to come out to be now? Well, I got to figure out how much current shoots through my path here. I know that for the whole wire that has a radius big R, its a current is I. Just how much goes through this part of the wire? Do you see what we're going to do if it's uniform? What fraction of the total current goes through this path? The total current is I, the fraction through this is what we want. You say, well, that just depends. What if the area enclosed was half of the cross-sectional area of the wire? Well, then it would be half the current, right? Because it's a uniform density. What if it was a fourth of the cross-sectional area? It would be a fourth of the current, right? So in other words, I could set up a little ratio. I could say, hey, my I in is to the total I, right? As the area in is to the total cross-sectional area of the wire. Does that make sense? And so rearranging this, I'd say, hey, that I in, the I total is just big I. It's just going to be I times the ratio of the areas. What's the area inside here? Well, this area here is the area of a circle with radius little r. That's pi little r squared. What's the area of the whole thing? Well, it's an area of a circle with a radius big R, so that's just pi big R squared. So my I in is just going to be I times little r squared over big R squared. This goes in there. So my current in, right? And that's just going to come out to be total current in the wire times R squared over big R squared. Now I move this 2 pi R over. Oops. I've got 2 pi R. And you say, okay, I can see that one of the R's is going to cancel. I'm getting mu naught I over 2 pi big R squared R. Okay? There we go. Now what I want to point out here is that for this problem, constant, 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 as I change my radius, what happens to the strength of the B field? It increases linearly with distance. What happens when I'm outside the wire? Well, outside the wire, it's just the same case as before, right? Mu naught I over 2 pi R. So it's proportional to R. I mean, inversely proportional to R. So what this looks like, right? Outside the wire, it's just a long wire, and I've got this field. Outside, the B is mu naught I over 2 pi R. So if I did a graph, and this was my B field strength, and this was R, my distance, and right here is big R, the radius of the wire. Inside is proportional to R. So as R gets bigger, B gets bigger, right? When R is 0, B is 0 at the heart of the wire, right? So my magnetic field strength, my graph, would start at 0. It would increase linearly until I got to the surface of the wire. Outside the wire, though, it's proportional to 1 over R. Yeah? And so it's going to drop off as 1 over R outside. That's my magnetic field strength inside the current carrying the wire. Okay. Can you guess what the next case would be that I would throw your way? You say, yeah, we found the field inside the wire. We already know the field outside of a long straight wire. You say, oh, he's going to ask. He's going to ask, hey, what if it was not a uniform current density? What if the current density was some factor, some function of R, right? Then you would have to do, right? I have to find my current that goes through there, right? So like maybe I would have some function of R. So when I do this, right, I can't just do a direct ratio, right? Because half the area wouldn't have half the current if the current is some function of R, right? So what I would have to do, the current outside, by the way, would still be mu naught I over 2 pi R, right? Whatever that total current is. But what I'm going to have to do is, what if they give me J as a function of R? So this is another case. What if J was a function of R? Like maybe, for example, what do you want it to be? Do you want the field density to be, the current density to be like increasing linearly, proportional to the square of the distance, proportional to the cube of the distance? Whatever, it doesn't matter. We'll give an example. Maybe J is like, I don't know. Hey, it's 4 R cubed, okay? All right? As this is just inside the wire. Obviously outside it's got to be 0. But I see, so maybe my current density, the charge gets more tightly packed as I head to the surface of the wire, and that might make sense because electrons want to repel each other. They kind of tend to congregate towards the outside of the wire. So it kind of makes sense. Maybe that's the case. Can you find the magnetic field strength as a function of R now? And you'd say, well, I would do the same thing. I'd make my path just like that. The left side would be the same. It's just a matter of how to calculate the current that's shooting through that path, right? Now before, I could just do a ratio. Half the area would be half the current, or a fourth of the area would be a fourth the current, and just do a ratio of how much cross-sectional area is inside the total. But I can't do that now, right? Because it gets more densely packed as I get outside. So if this was if this was a third, say, of the total cross-sectional area, you say it wouldn't be a third of the current, it'd be less than a third, because the current gets more densely packed for the outside. And so you say, so how do we fix this? You say, well, we're going to have to do a little calculus, yeah? Right? Calculus in our calculus here. You say, what we're going to have to do is, J is a function of R. I'm going to have to go slice, right? Slice up this area and add up the the current flowing through each little sliver of area, right? How should we split this up? Are we going to split it up like this in a horizontal slice? No. We would like every slice to be at a constant density, so it's got to be at a constant radius, right? We're going to do little concentric circular slivers, right? So we're going to slice this up, this area in there. We're going to slice it up like slice, 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 right? And we're going to have to find the current in one slice going around, right? That slice has a little dA, right? A little d area. Yeah. You say, what's the area of that slice? Because what I'm getting here is I'm getting that J is the current per area. So it's, if you want, this slice carries a current dI. Yeah. In that area, dA. You say, this my current to area ratio is J. And so rearranging, that would also be dI over dA would be J. So rearranging, this is just like when we use lambda and sigma and rho, right? And so rearranging this, dI is J dA. All right? And I'm going to add up all of the little dI's through all the little slivers here, right? Until I get to the bound here where I'm trying to find where my path is, where my Amperian path is. And so doing this, I would say, hey, dI, and again, it's going to be rho, it's going to be that, right? And so you say, hey, what's dA? Well, I take this sliver, right, this, which is a little ring, right? How thick do I want that ring to be? Infinitesimally thin, right? Because I want everywhere on that sliver to be at the same R value, so it's the same density, right? So it's got a thickness dr, right? If I slice it and unroll it, it would look like this, right? There's that sliver. It has an area dA. And you say, hey, the thickness here, that's dr. What's the length here? Well, that's the distance around, right? That's 2 pi little r that I'm at, yeah? Right? Some variable r, right? And so dA is just length times width. You say dA, the area of that one sliver is going to be 2 pi r dr. Put that in here. The little bit of current will be the current density times 2 pi r dr. Yeah. And so now, to find the current that's going in through this path, I would just integrate. Yeah. And I'm doing the path from where to where? From r equals 0 out to r equals little r, whatever radius inside I'm trying to find the B field. Yeah. Okay, and that's it. Now the J, if J was constant, the J would kick out. You know what this would end up being? I just had pi r squared, J times pi r squared. Anyway, but J times the area. It would be the current, right? It's J times the area. Current density times area is the current, right? So you say, but because J is a function of r, I would now stick this function in there and integrate. Okay. Once I have that, that's my current. That's what then goes in here, here for current instead of just big I. Yeah. All right. Okay. Maybe the current in there. So I get whatever I get out here for current divided by 2 pi r times mu naught. That's what I get. Okay. Good enough. All right.